Welcome to chemistry lesson 5.04, the second part of periodic trends. This video, we're going to talk about atomic radius and electronegativity, which are our last two periodic trends. So we left off last time and with ionization energy and electron affinity, and we said they're kind of the same thing. It's like saying if you had a dozen donuts, I ate still talking about the same thing. So what we're going to talk about here is atomic radius. And atomic radius is defined as the distance, I'm flatten up my paper here, distance between, average distance, between two nuclei of the same atoms. So when bromine's diatomic, boy, that was a really bad start to my notes there. It's a little sloppy. So if I have diatomic bromine, I take the distance between the two nuclei of bromine and I divide it by 2. Well, why don't we just say from the nuclei to the outermost valence electron? Remember, electrons are sketchy and they don't always like to be where they're supposed to be. So it's more accurate to take the average of the distance between two nuclei. Well, how does this change from top to bottom and from left to right? Well, top to bottom is pretty apparent. So let's go back to lithium. So I had lithium. We said that was 1s2, 2s1. And then I had rubidium. And rubidium, which is down here. So I have rubidium, it is 3 from the bottom. And I have lithium, which is here. Rubidium is 1s2, 2s2, 2p6, 3s2, 3p6. It would actually be 3d10 and then 4s2, 4p6. And then we go to 5s1. Well, think about it. If this is my nucleus back here, so if this represents the nucleus, and this is my valence electron, and radius, in a sense, theoretically, we can think of radius as the nucleus to the valence electron. It's just that that's difficult to measure. So look at my radius here. That's pretty short. Look at my radius here. Wow, that's a lot bigger because we added all of those electrons. And so what happens is, as I go from the top of the table to the bottom of the table, I add a lot of orbitals. My radius is going to increase. Now, you would think commonsensically that as I go across, so here I go 2s1, now I'm going to have 2s2, now I'm going to have 2p, and I'm adding electrons. So you would think I'm going to increase the radius as I go from left to right. But that actually is not the case. There's another factor at work. So as I go from left to right, it's true, I am adding electrons, but I'm also adding protons. So as we go left to right, I am adding protons and electrons. So you would think that because I'm adding electrons, my radius would increase, but actually what has the most effect on radius is the fact that as I go from boron to carbon has 6 protons, nitrogen has 7 protons, that has a bigger impact because these protons, remember, have a positive pull and they pull on the electrons. So the additional pull of the protons is greater than any distance that's created, by the electrons. In other words, as I go across, I experience a greater positive charge and it actually pulls the electrons closer to my nuclei. This phenomenon is called effective nuclear charge. Effective nuclear charge. And so what happens is over here with fluorine, my 9 protons pull my electrons in tighter. And so this actually has a smaller atomic radius than beryllium or lithium. And so what happens because of effective nuclear charge is my atomic radius increases as I go from the right to the left. And then of course it increases as I go from the top to the bottom because I'm adding electron shells. But this is a little bit counterintuitive. Okay, our last one that we're going to talk about, and I'm going to pause because I have to swap sheets. You guys have to turn your page, is electronegativity. Still not pausing. Okay. Okay, so here we are with electronegativity. So ionization energy and electron affinity deal with giving or taking electrons. And so let's just kind of recap that. So I have ionization energy and electron affinity deal with giving and taking electrons. I think I better take my paper down. It's a little bit bouncing around on me. Giving and taking electrons. And what we're going to see later in the chapter, that happens when we do an ionic bond. But sometimes atoms don't give and take electrons, they share. And electronegativity only comes into play when we're dealing with atoms that share electrons. So in a covalent bond, which is sharing electrons, so all of this deals with in a covalent bond. So we're not talking about an ionic bond. And electronegativity is the ability of an atom to pull electrons towards its nucleus. The ability of an atom to pull electrons towards its nucleus. Well, we have the same behavior patterns as ionization, and the reasons for the behavior patterns are the same as ionization energy and electron affinity. So we've said over here we're trying to lose electrons. And we said over here we're trying to gain electrons. The opposite law, and we're pretty much always talking about these guys when we're talking about electronegativity, because these guys actually, it's kind of here, these guys are the only ones. So I really shouldn't have this whited out. That's a mistake. I should not have colored this in because these guys don't covalent bond. All right, I'm just going to kind of white that out so that we can pretend like I didn't do that. Only nonmetals really covalent bond. Okay, so we're talking about these guys. But hydrogen, of course, is the exception. So if I put, so this guy's fluorine's desperately trying to gain electrons. So let's talk about left to right. Hydrogen wants to lose electrons in the worst way. So because fluorine has a tendency and chlorine want to gain electrons, they will pull, even though they're sharing, they'll pull the electrons towards their nucleus. It's a little bit like if you've ever shared covers with somebody who's a cover hog. These guys are cover hogs, and these guys are kind of running hot anyways. They kind of want to get rid of the covers. So it's the same reasons we talked about with ionization and electron affinity, but we increase in electronegativity as we go over to the right of the table. And again, these guys, the nucleus isn't pulling as hard on the valence electrons, and so we increase as we go up. So all three of these have the same trend and for the same reasons. It's not enough to memorize the trend, you also have to know the reasons. So what that means is we're going to write something called Lewis structures here in a short while. If I have hydrogen and chlorine bonded together, and this represents their sharing a pair of electrons, the chlorine are going to pull, it's not going to take the electrons away from the hydrogen, but the electrons electrons will kind of hang out over here closer to the chlorine than they will closer to the hydrogen. We represent that with an arrow and a little positive sign at the end. That means that we're sharing, but this guy has less, this guy has more, so we have a little bit of a negative sign here and a little bit of a positive sign here. It's not a full positive, it's not a full negative, but it's a partial. Same thing if I put nitrogen and, well, let me look at it. Let me show you water, because we're going to talk about this later in this chapter. I've got H2O, and the oxygen is more electronegative. Oxygen's going to be here. It's more electronegative than the hydrogen, and so it pulls the electrons towards its nucleus. So the electrons like to hang out here a little bit more than they do down here. So that gives my hydrogens kind of a positive charge and a partial positive charge, and my oxygen a partial negative charge. And this is huge. This creates what's called a polar molecule. More on that later. But again, our takeaways here are ionization and electron affinity. We're completely taking away or completely giving an electron. Here we're sharing. But the rationale behind it is still these guys are trying to lose and these guys are trying to gain. And you need to be able to explain that, maybe even in a paragraph essay. All right, those are our last two periodic trends. We're going to do the second half of this chapter, a little bit of bonding work. So thanks for watching and have a good day.